Okay, in today's video, I'm going to go over drawing ray diagrams for convex lenses. And this is going to be our general setup that we're going to use, and this is, I think, what you see most of the time in the textbook. Here we have our convex, or our converging lens, and we have some parts of this diagram I think that we should just be aware of. One of them is the principal axis. This is this white line that runs horizontal through the center of the lens. Then we have our focal point, and we have the point we call 2f. And the focal point is at a distance of one focal length from the lens, and 2f is twice as far away. So f is from one focal length away, and 2f is twice as far away. And this is a biconvex lens, so there is an f, a focal point, and a 2f on each side of the lens. And what we want to be able to do at the end of this video is you should be able to draw the ray diagram to locate the image for any place that we were to put the object. So this green arrow is our object. We're going to start beyond 2f. Then we're going to put the object at 2f. Then we're going to put it between f and 2f. And then f, and finally inside of f. And for any case, you should be able to draw the ray diagram to locate the image. And you should also really know where the image will be beforehand. You should really know that before you actually draw the ray diagram. You should have a sense about where the image is going to be. You should have a sense about what the size of the image is going to be relative to the object, the orientation, and the type. Is it going to be a virtual or a real image? Okay, so let's go through and get started. Here is our first problem. You can see we have our object right here. It's at a distance DO, the object distance, greater than 2f. And we're going to draw the ray diagrams to locate the image. Now before we get started, we're going to go over the convex lenses in this video, and then we'll do concave mirrors in the next video, and then concave lenses and convex mirrors finally in the fourth video. And you should really notice that for all of the ray diagrams, for all four of those optical objects, both mirrors and both lenses, the ray diagrams are really drawn basically exactly the same way. There's slight variations to how you do it, but we can use the same rules for all four of those types of lenses and mirrors. So you don't have to really memorize all of them. You just have to know how to apply the rules to each case. And in each case, the rules are basically the same. Okay, so let's get started. We're going to draw three rays to locate the image. This is the object, this is the lens, this is your eye. We have to draw three rays that come through the lens in the direction of your eye so that you can locate the image. The first ray we draw is the parallel ray. It enters the lens parallel to the principal axis. So once again, this is the principal axis. This is the first ray. You can see those two are parallel. We draw the first ray parallel. When it comes out of the lens, it's refracted or bent in such a way that it goes through the focal point. It must go through this point. It's not just some random bend. It goes through the focal point. So that's the first ray. I like to call this one parallel F. The next one is kind of the opposite. It enters the lens going from the object through the focal point. So it must go through the focal point. It starts at the object, goes through the focal point, strikes the center of the lens, and comes out parallel. So this one I like to call parallel F. And the third one is the one we draw that goes straight through the center, and the image is going to be located where those light rays converge, and that is our image. Okay? Now, we want to summarize where is the image and all the information that we want to know about the image. In this case, when the object is greater than 2f away, the image will always be somewhere between f and 2f. The image will always be smaller than the object. The image will always be inverted or upside down, and will always be a real image. Okay? So we've completed that problem. I'm just going to review this one really quick, and then we'll go on, and we won't take as much time for the next one, so we've got four more to do. So we drew the ray diagram. We drew the first ray, parallel F. Then we went F, parallel, has to go through F, has to go through F, has to be parallel, and has to be parallel to the principal axis. This one goes straight through the center. It goes through the center of the lens. It is not bent. It is not refracted. And the image will be located at the where those three rays intersect. We started at the point. Therefore, that's the image of the point. And this is the information that we drew from our that we got from our ray diagram. Okay, let's go on and do the next one. Now you can see the object distance. The object is exactly 2f from the lens, parallel f, f, parallel, straight through the center, and that is our image. You will notice when the object is at 2f, the image will always be at 2f. The image distance is 2f. It has to be there. The image will always be the same size. When your object is at 2f, the image is the same size. It will always be inverted or upside down, and it will always be a real image, an image that is created by converging light rays. Okay, here's the next one. Now we've moved it a little closer. Now we're between f and 2f. Parallel f, f, parallel, straight through the center. There's our image. The image is going to be beyond 2f. So now when the object is between f and 2f, the image is going to be greater than 2f away from the lens, always. The image will always be bigger. First it was smaller, then it was the same size, and now it's magnified, it's bigger. But it will always be inverted, and it will always be a real image. Okay? Now, the next one is a little bit of a different case, although we're going to apply the rules the same way. Now the object is at f. We've gotten closer. The object is right at f. We're going to draw the first ray the same way. Parallel out through f. Now, we can't really draw the second one because that would be the f parallel. We would go straight down and we wouldn't really go parallel. It doesn't go through the lens. It doesn't come towards our eye, so we're going to ignore it. But we can draw the third one. We're going to draw the third ray that goes straight through the center of the lens like that. Has to go through this point. You will notice these light rays are parallel. Parallel light rays don't intersect. In all of the previous cases, the image occurred where the light rays intersected. So, no intersection, you guessed it, no image. So when the object is at 2f, there is no image because the light rays are parallel. Okay? Last one. Now we've brought the object inside of f. We're inside the focal point. This is the focal point. We're inside the focal point, and we're going to draw the first ray exactly the same. Parallel, f. Once again, we can't really draw, we can, but we wouldn't really use it to locate the image, the one that goes through f. One goes like this, but it doesn't go through the lens. It doesn't come to our eye. We don't see it, so we don't really need it. But we can draw the third one, which goes straight through the center. You'll notice it goes straight through the center. It has to go through the center of this lens. Now you will notice these light rays are not converging. They're not parallel. They are diverging. These are diverging light rays. Your eye is over here. It sees these diverging light rays coming into it. Your brain does not know that this light ray made this bend. It was not refracted right here. So it assumes these light rays travel in a straight line, and it follows them back looking for the intersection. And you will notice, if we trace them back, you will notice that they actually converge behind the lens, and that is where the image appears. Now you'll notice something in this case. It's behind the lens. It's on the other side. The other images were always between our eye and the lens. This one is on the other side of the lens, behind the lens, not in front of the lens. And that's our image. The image, when you're inside the focal length, when the object is less than f away from the lens, will always be behind the lens. It will always be magnified or bigger. It will always be right side up. Now it's switched from inverted to erect. And this is called a virtual image. A virtual image is an image that is created by diverging light rays. So this is what we call a virtual image. The light doesn't actually come from here, but that is what we call a virtual image produced by diverging light rays. Okay, and this is actually what we have. This is called a magnifying glass. When you use a magnifying glass, you bring the magnifying glass, the lens, really close to the page if you're looking at a piece of paper, whatever you're looking at, and it looks in right side up and magnified. That's called a magnifying glass. Okay, so we've gone through all 5 cases. You can now draw the ray diagrams for any case to locate the image using a convex lens. Now, I'm going to go through this one table. Looks a little confusing, to kind of summarize what we learned in our ray diagrams. This is for a convex lens. This is for a concave mirror. It's going to be in the second video of this series, but I want you to compare the answers for the convex lens to the concave mirror. This is the object distance. These are the 5 that we went through. Here's the image distance, the orientation, the size, and the type. Now here's the same thing for the concave mirror, which we'll do in the next video. Here's the object distance. There's 5 of them. Here's the image distance, the orientation, the size, and the type of the image. You will notice we have 2F, 2F. This is C and C. C is the analogous point for a concave mirror. This lens has a focal point. This mirror has a focal point. This has 2F, which is twice as far away from the lens. This has C. It's the center of curvature for a spherical mirror. It's the same thing. It's the same kind of point. It's analogous to the 2F on the lens. Okay? So you should notice these are the answers that we came up with as far as the information for the image. You should notice that the answers on this table for the convex lens and the answers on this table for the concave mirror are exactly the same. For example, when the object is at 2F, the image is at 2F. When the object is at C, the image is at C. When the object is at 2F, it's inverted, it's the same size, and it's real. When we're at C, it's inverted, the same size, and real. So all of the answers are the same. Another example, when you're at F, no image. When you're at F, no image. So you don't have to memorize all of the answers or 10 different sets of answers for the convex lenses and the concave mirrors. If you know the pattern for one, then you'll know the pattern for the other, because the answers are exactly the same, except we have a point we call 2F, and when on the mirrors we have a point that we call C instead of 2F. Okay? So please, I think if you try and draw those diagrams, the ray diagrams, look at the pattern that develops with respect to the object information and the image information. You'll notice there's a pattern that develops, and you don't have to memorize everything. Just learn the pattern and learn the rules. Okay? So thank you very much. I hope that was helpful, and we'll see you in the next video.